Welcome to our presentation about memory management model of the MIPS64 architecture. There will be 4 parts in our project, include introduction, evolution of the MIPS architecture, recap the concept of packing, MMU, TLB, and page table, and then the reference. So let's start with the introduction to MIPS64. MIPS64 is a 64-bit version of the MIPS processor family. It follows the RISC model to optimize performance. MIPS64 supports 64-bit data and array processing, making it well suited for high-performance embedded system and network applications. Some notable features of MIPS64 include modularity, scalability, and impressive energy efficiency. As you can see, here is a graph for the evolution of MIPS64 architecture. The first release a bit in 1985, and after many updates, in 2014 is our main focus. MIPS64 released the latest version covered in our analysis. Fundamentally, MIPS64 employs a baking mechanism for memory management. As mentioned, MIPS64 essentially utilizes a baking memory management scheme. Baking is a memory management technique that allows process physical address space to be non-contiguous. To clearly understanding, let's examine the related concepts. The first one is virtual address, VA or logical address. This is the address the program uses. MIPS64 supports a virtual address space up to 64 bits, with values ranging from 0 to 2 to the 64 minus 1. Then the second concept, physical address PA, which represents the actual address in physical memory. MIPS64 supports a physical address space up to 59 bits, with values ranging from 0 to 2 to the 59 minus 1. MMU, Memory Management Unit, play a crucial role in mapping address from each program to distinct area of memory. This is feasible because physical memory is often considered smaller than theoretical limits, and each program has unique memory usage patterns at any given time. Then TLB stands for Translation Localized Buffer. It's a specialized memory cache that stores recent translation of virtual memory address to their corresponding physical address, thus enabling faster memory retrieval. Then the last one is page table, which is a data structure that employs to store the mapping between virtual and physical address. About the concept of paging and base size, virtual memory is divided into fixed size blocks, no updates. The default base size on MIPS64 is 4 KB. However, to cater to specialized requirements, MIPS64 also supports optional base size of 1 KB and 256 MB. It's important to note that these sizes do not replace the default 4 KB size. Instead, they complement specific applications, for instance, long space for extensive datasets. And
now, continue talking about TLB, stand for Translation Localized Buffer. This purpose is to cast virtual to physical address translations, thereby avoiding repeated and time-consuming page table lookups. About structure, it features a fully associated cache architecture, where all entries are assigned in parallel to file march. The size is configurable, ranging from 1 to 64 entries, depending on the specific implementation. Next, TLB entry details. Each entry within a MIPS64 TLB comprises 2 logical components, a comparison section and a physical translation section. The first one, comparison section. This part is used to map addresses, specifically page numbers, and includes the following fields. It includes region code. This field specifies the mapping region. Bits 6362 of the virtual address must match this field for successful comparison. Virtual page number, VPN2. This represents the high order bits of the virtual address, effectively divided by 2 because one TLB entry maps 2 pages. The next one, address space identifier, ASID. This field identifies the specific process to which the virtual address belongs. Global bit G. If this bit is set, the ASID comparison is ignored, allowing this particular TLB entry to be shared across all processes. And the last one, page mask. This specifies the size of the page or pages that this mapping represents, supporting variable page size ranging from 1 kilobyte to 256 megabytes. The second is physical translation part. This section contains the physical mapping, which is the frame number and includes the fields. First one, PFN0 and PFN1 stand for physical frame number. These are the physical frame numbers for even and odd pages, respectively. Next one, valid bits V. This bit indicates whether the TLB entry is valid. If it is invalid, a TLB invalid exception is raised upon access. Dirty bit D. This bit indicates whether write operations are permitted to the corresponding page. If it's not set and a write operation occurs, a TLB modify exception is triggered. Next one, RIXI bits. This is read inhibit, execute inhibit optional. These bits enable finer grain protection for virtual memory pages, including the ability to create write only on non-executable pages. About RI, read inhibit bit prevents load operation from this page. A violation results in a TLB RI exception. Next one, XI executed inhibited bit prevent fetching instruction from this page. A violation leads to a TLB XI exception. And the last, catch attribute. Attribute C. This field specifies the catching behavior for the page, such as write back or write through. About TLB, the reason for having two translation entries, PFN0 and PFN1, for each TLB entry is that each TLB entry masks a pair of archived virtual pages, and these two physical translation entries correspond to the even and odd pages of that pair. The selection between PFN0 and PFN1 is determined by the least significant bit of the virtual address that is not part of the page mask. Furthermore, each TLB entry has its own page size, which can range from 1 kilobyte to 256 megabytes in multiple.
Let's now dive into a detailed address translation process. When a virtual address is accessed, the system goes through a series of steps to convert it into a physical address. Step number 1, the system begins by extracting key components from the virtual address. These include the virtual page number VPN, the region bits, the address space identifier access. Step number 2, using this information, the system searched through all entries in the TLB to find a match. A match is determined by the following conditions. The region bits, specifically bits 63 to 62 of the virtual address, must match the R field of a TLB entry. The mask VPN must match the VPN2 field of the entry. The page mask specifies which bits are ignored in this comparison. The access must either match the access field in the entry or the entry must have the global G bit set, which makes it valid for all access. Step number 3. Once a match is found, the system proceeds as follows. The appropriate PFN is selected. PFN0 for even pages or PFN1 for odd pages, based on the even odd bit inferred from the page size. The final physical address is then calculated by combining the PFN with the offset within the page. Several exceptions may still occur at this stage. If the valid V bit of the matching TLB entry is 0, a TLB invalid exception is raised. If the access is a write and the dirty D bit is 0, a TLB modified exception is triggered. If the read inhibit RI or execute inhibit XI bits are set in the matching entry and the access writes violate the restrictions, the corresponding TLB RI or TLB XI exceptions will be generated. If no match is found in the TLB, a TLB refill exception is triggered, indicating that the translation for the requested virtual address is not present in the TLB, and that the virtual to physical address mapping must be fetched from the page table. Here is a quick summary of the types of exceptions that may occur during the address translation process described above. TLB refill. No corresponding TLB entry was found for the virtual address. TLB invalid. A matching TLB entry was found, but it was marked as invalid. TLB modified. An attempt was made to write to a page that was not marked as dirty, meaning writes were not permitted. TLB-RI or TLB-XI. An attempt was made to reach or fetch an instruction from a page that was restricted by the read inhibit RI or execute inhibit XI bits, respectively. Double fault. A TLB exception occurred while another TLB exception was already being handled. Beyond the TLB, let's take a broader look at how the CPU accesses memory. The address of the required data is generated in the execution unit or instruction fetch unit of the processor. Subsequently, most of these addresses undergoes translation from virtual to physical via the TLB. However, it's important to note that certain address ranges bypass the TLB and are not subject to this translation process. The majority of addresses are present to the primary cache, which resides on the processor chip. If a copy of the data corresponding to the address is found within the primary cache, it is returned immediately. Conversely, certain address ranges are never brought into the cache. The addresses are directed straight to the system bus. In the event that the primary cache does not contain the requested data, the address is then presented to the secondary cache. If the secondary cache holds a copy of the data, it is returned promptly. The size and architecture of the secondary cache can vary significantly between different CPU models, and some CPUs may not even incorporate a secondary cache. Following a miss in both the primary and secondary caches, the address is placed onto the system bus. The memory module that recognizes the address then placed the request data onto the bus, allowing the processor to retrieve it.
So, let's explore how MIPS64 organizes its virtual memory into distinct segments that control access, privilege levels, and memory mapping. While each virtual address in MIPS64 is 64 bits, not all of these bits are directly used for addressing. Instead, the top two bits 63 and 62, are crucial. They determine which memory segment the address belongs to. The MIPS64 defines four main segments, each with its own rules for translation, access, and caching. Segment 1, Exclusive, the user segment. That is the user space labeled with region code 00. It is mapped using the control translation register and can be accessed in both user and kernel modes. It supports up to 16 terabytes of virtual address space and is where user-level applications primarily operate. And now, moving into the more privileged territory. Segment 2, XKSEC the supervisor segment, marked with region code 01. The 8K sets is mapped through the TLB, the translation look-aside buffer, and can be accessed in kernel or supervisor mode only. And although it is not commonly used in 64-bit implementations, it still defines 2 TB space in theory. Next, we'll leave the virtual memory altogether and go straight to hardware. Segment 3, XKPHIS, the physical address segment, with region code 10. The XK files provide direct access to physical memory, meaning that it bypassed by the TLB entirely. The segment is used exclusively by kernel and spans 1 TB of physical memory. It also allows cache control, letting the system decide whether memory should be cached or not. And finally, the heart of the kernel is virtual memory operations. Segment 4, KSEC, the kernel virtual segment. The region code 11 marks this segment, and it is mapped to the TLB, accessible only in kernel mode, and commonly used for kernel memory application and device drivers. The KSEC provides 2 TB of space, although some sources prefer a 16 TB kernel virtual space that is both mapped and cached. So, what really sets this segment apart? Each one defines whether memory access is mapped or direct, whether it's accessible in user or kernel mode, and whether the memory can be cached. By simply inspecting 2 bits, the system knows how to translate, who can access, and how to treat every address in memory. And that is the power of MIPS64 segment memory module. Part 4, References. The information in this presentation was carefully gathered from official MIPS documentation, including the MIPS64 Architecture for Programmers series, academic course material, and structured technical resources, and public reference manual from MIPS Technologies. And we also refer to well-documented sources such as Wikipedia and a helpful reference by Alan Clemens. A complete list of 9 references included in our report and available at the end of this presentation for further reading. And our project was collaborative effort by 4 team members. Nguyễn Hoàng Hà focused on gathering and analyzing official documentations. Phạm Thùy Anh prepared for LaTeX document. Lê Hải Đông Nhi wrote and structured the script. And I, Đinh Vân Anh, compiled the final presentation and added today's content. And that is the end of our presentation today. Thank you for watching, and we hope this gave you a solid overview of memory segmentation in MIPS64 and how region codes shape access, mapping, and privilege in the architecture. If you have any questions and would like a deeper dive into any segment, I'll be happy to discuss it further.